Namaskaram everyone. Welcome to another day of webinars. And I take immense pleasure in welcoming you all for the first session of Mathematics 1A webinar. Today you will be having two more subjects after this. Today's topic is functions and lesson 1, which will be handled by our own PGT Mathematics from TSMS Velimala, Arsipuram Sangareddy district, Mrs. USHA Madam. Mrs. USHA holds a master's degree in mathematics and a B.Ed degree. She has over 20 years of experience in teaching mathematics for intermediate students. Students, you are very lucky to have Usha Madam taking functions for you. And she has been associated with model schools from 2013, according to her principal. And the experience that we had with Usha Madam during the second year webinars, we can proudly say that she's industrious and she has proved herself in terms of laudable results also. She has been instrumental in carving a night for Telangana Model School Velimala, Arsipuram, by shouldering the responsibility in each and every activity of the institution. She has also received the Best Teacher Award in 2018 at Mandal level. Usha Madam, over to you. Welcome for another interesting session on functions. Hope our junior intermediate students also get benefited because of your session. Over to you, ma'am.
Thank you, madam. Good morning, everyone. And I welcome you all children to Mathematics 1A functions topic. Right? It's my immense pleasure to share my knowledge with you. Let us start with the functions topic. The topic itself, it's a new topic, but even then, you need not get scared, right? So we'll try to make it as easy as possible so that you can enjoy the subject. Right. Now, today's topic, the topics what we are discussing will be the definitions of ordered pair, Cartesian product, relation, function, domain, what is domain, codomain, image, pre-image. See, all these definitions, they are prerequisites to understand the topic, right? So once you understand this, throughout the chapter, we are going to make use of these terms. So you need to understand these definitions. And then we are going to discuss types of functions, which are 1-1, onto, and bijective functions. We are also going to deal with the theorems which are related to the concepts 1-1, onto, and bijections. And we will solve some problems based on these concepts. Right? Now, before we start with an ordered pair, you are familiar with the definition of a set, isn't it? In class 10, you have studied the concept called sets. What is a set? A set is a well-defined collection of objects, isn't it? You have already seen that. Now, when we talk of an ordered pair or any term which we are dealing in today's topic, we are not confining ourselves to one set. We will take two sets. On two sets, we will define a Cartesian product or a relation or a function, right? So let us start with the first definition, that is ordered pair. What is an ordered pair? If A and B are two sets and A belongs to set A and B belongs to set B, then A comma B is called an ordered pair. It is an ordered pair, right? Now, what exactly is the meaning of this statement. See, A is it is an element which is taken from the first set. B is an element which is taken from the second set B. Now, any element from A which is taken as the first coordinate and element taken from second set taken as the second coordinate, and you're pairing them. When you pair them, you call it as an ordered pair. And remember, the first element is coming from the first set, and the second element which is placed, which is taken from the second set. All right, children, this is a simple definition. Like you have two sets, one element is coming from the first and the other element is coming from the second, and the order is very important, right? Now, the next definition is the Cartesian product. Now, let us see what is a Cartesian product. Let A and B be two sets, then A comma B such that A belongs to A and B belongs to B. Now, just observe the brackets what I'm taking, the braces what we have taken here. A comma B, what is it? It is an ordered pair. Just now we have seen. Now, what is that you are taking in this set? Set of all ordered pairs you are taking, where the first coordinate is coming from the first set and the second coordinate from the second set. So let A and B be two sets, then A comma B such that A belongs to A and B belongs to B is called a Cartesian product of A and B, and is denoted by A cross B. Now, Cartesian product of two sets A and B will be denoted with A cross B. Right, children? I want you to just observe a small point over here. You have two sets. The Cartesian product, it is a set of all the elements. How are the elements in the set? The elements in this Cartesian product, I mean A cross B, are ordered pairs. Like in our previous classes, we were discussing elements. Now here, the element is an ordered pair, right? And how you are taking the ordered pairs? All the combinations, like whatever elements you have in set A will have a mapping in set B. Okay, that's how you will relate and you will take as an ordered pair. Now let us try to understand this with an example. Now let us take two sets, children. Set A has got three elements, 1, 2, 3, and set B has got A and B as elements, right? Then when you write A cross B is the Cartesian product, right? And just now I said, whenever you are writing Cartesian product, you will be getting ordered pairs placed inside a set. Okay, and how are the order pairs? Now, suppose if you take 1 as the element in the first set, 1 will be paired with A, 1 will be paired with B. Likewise, each and every element in set A will be paired with each and every element in set B. Okay, so all such order pairs placed in the set, we call it as A cross B. Now let us see what it is. Then A cross B is equal to 1 comma A, 1 comma B, 2 comma A, 2 comma B, 3 comma A, and 3 comma B. Just now I was telling, isn't it? Every element is paired with each and every element which you have in the second set. All right, children. So this is Cartesian product. Now let us go with the next definition, that is relation. Okay, what is a relation? What is a relation? If A and B are non-empty sets. Non-empty sets, what do you mean by non-empty sets? The set which has got some elements in it, isn't it? So if A and B are non-empty sets, then any subset of A cross B is called a relation from A to B. Now, what actually is the meaning of this? Now, A cross B is a Cartesian product. Just now we have seen. Now, when we were writing the Cartesian product, each and every element which you have in set A has got some pair in the second set, right? Now, you can take the total Cartesian product A cross B, or you can take a subset of A cross B to define a relation. So if A and B are non-empty sets, then any subset of A cross B can be taken as a relation from A to B. Now let us try to understand with an example. So A is equal to 1, 2, 3, the same example I'm taking, children. Then A cross B, that is 1 comma A, 1 comma B, 2 comma A, 2 comma B, 3 comma A, and 3 comma B. This is what is the Cartesian product, right? Now we can take any number of relations on this Cartesian product. Why? Because we are taking subset of Cartesian product, right? Now you can see two different relations here. First one, F is a relation. Now I'm just taking only a subset of this, that is 1 comma A and 1 comma B. This is one relation. And you can also take G as a relation by taking 2 comma A and 3 comma B. Likewise, you have H. H is another relation, which is 1 comma A, 2 comma A, and 3 comma A. That means, see, is it that we have to confine only with these three relations? No. You can take all possible subsets or total of A cross B to define it as a relation, right? Now let us try to see the same thing diagrammatically. Now you have set A with elements 1, 2, 3, right? And we are taking the second set with elements A and B. Now, one is we are defining F as a function. See, this is the explanation what we are taking for the first bit, I mean the first relation, right? Now in F, how is it related? One is related to A and one is also related to B. It is mapped to B, right? And let us see the second one. The same thing, like we are taking two sets A and B with elements 1, 2, 3 and AB respectively. And over this, we are defining a relation G. Now in this relation G, 2 is mapped to A and 3 is mapped to B. Right, children? Now let us see the last one also, that is the, H. Again, we are taking the sets A, that is A has got the elements as 1, 2, 3. B has got the elements as AB, right? Now, you are just defining H as a relation, then 1 comma A, 2 comma A, 3 comma A. This is a relation. Now, let us try to have a comparison of all these three before we go to the next concept. Now, in the first example, what we have taken, the element in the first set is related to many elements in set B, isn't it? So we can say this is one to many relation, one to many relation, right? Now, in the second example, what we have seen, every element in set A has got only one mapping. That means it is related to only one element in the second set. So we can also say this as a 1-1 relation. Be specific. Okay, this is a relation what we are talking. And then the third example what we have seen. See, all the elements what you have in set A, they are related to only one element in set B. That means these are many which are related to one. So we can say this is many to one relation. Now, why this example is important? We are trying, after I define the next definition, right? We will have a comparison between a relation and a function, children. All right. So you need to be very clear in your mind, like what is this one to many relation, 1-1 relation, and many to one relation. Hope I am clear here, right? So let us continue with the next definition, that is function. Now here comes the main topic, that is function, as our title was telling, right? What is a function? Now, when we talk of a function, first of all, it should be a relation. Now, on the definition of a relation, we will try to put some conditions to get a function, right? Now, let us see what it is. A relation F from a set A to set B is said to be a function or a mapping from A to B if for each A belongs to A, for each A belongs to A, there exists a unique B belongs to B such that f of A belongs to such that A comma B belongs to F. It is denoted by F maps A to B. We will denote it as F maps A to B. Now we will try to understand this definition word by word, children, right? So a relation F, that means for a function, first of all, it should be a relation. And how is this relation? Relation is from set A to set B. Okay, then how is that relation becoming a function? By following this condition. What is this condition? For each A belongs to A, that means every element which is there in set A, it should have a unique mapping in set B. That means it should be related to some element in set B. And this word is very important. For each A belongs to A, that means every element in set A should have a unique element in set B, where you can write it as an ordered pair, that is A comma B, which belongs to the function. So we denote this function by saying F maps A to B. That means F is a function which is defined from set A to set B. All right. Now we will see a diagrammatic representation for this, children. Let us take set A with elements 1, 2, 3, 4. Okay. And set B with elements A, B, C, D, E. Right? We are defining a function F. Now, how is this function? 1 is related to B, 2 is related to C, 3 is mapped to D, and 4 is mapped to E. Right? Now, I want you to throw some attention on this diagram. If you can observe carefully, each and every element in set A has got some relation. Are you observing? Right? No element in set A is left free without any mapping. Hope you are able to follow this, right? Now, this is a very important condition for any relation to be a function. So every element in set A should have a mapping it should be related to at least one element in set B. Then we can call it as a function. Now, how to check whether the given relation is a function? Now we have a condition to check this, children. If F maps A to B is a function, then for A1 and A2 belongs to A. You're taking two elements A1 and A2 from the first set. And if that A1 and A2 are equal, then it means F of A1 is equal to F of A2. Let us try to understand this statement. Now, here, children, what is this F of A1 and F of A2? An important thing, right? Now, let us try to have this explanation through this diagram itself. Now, F is a function. Now, in this function, if I am substituting 1, right, then the answer is B. That means this B is nothing but F of 1, isn't it? F of 1 is B. Likewise, F of 2 is C, and F of 3 is D, and so on. So if A1 and A2, if they are equal, what are A1 and A2? A1 and A2 are any two elements at random. We are picking from the first set. And if you are substituting that in the function, then the answer what you are getting, F of A1 and F of A2, they should be equal. Then you can call it as a function. Hope that the concept is clear. Then let us try to understand it with some more terms. That is the domain of a function. What is a domain? Let F maps A to B be a function. Then the set A is called domain of F. Also, we have another definition, that is codomain. What is codomain? If F maps A to B is a function, then set B is called codomain of F. Now, what exactly is this? Now, A and B are two sets, children. On these two sets, you are defining the function F. All right. Now, this function f has got two sets. The first set A, you're calling it as domain. And the second set, what you're taking, we are calling it as codomain. Now, let us see the same thing as a diagram. Now, I'm taking set A and set B, right? You're defining a function f over these two sets. Then the first set, I mean the total, whatever you're taking in set A, the totally it constitutes domain. And the second set, we call it as codomain. This is very simple, right? Two sets, first set is domain, second set is codomain. Now, we'll move further with the next definition. F maps A to B is a function and f of A equal to B, then B is said to be the image of A and A is said to be the pre-image of B. Now you have two sets A and B over which you are defining a function f, right? Now f of A, that means what you're doing, you're taking an element from the first set, you're substituting in the function, then you're getting some answer. That answer is B, right? So that answer what you're getting, B is called as image of A and A is called pre-image of B. That we will try to see with a diagram. Now, before that, we will go with the next definition also, that is range. The set of all images of the elements in the domain of a function is called range of a function. Now, what exactly is this? The set of all images. See, children, when you are taking two sets, now let us talk about first set. First set may have any number of elements, right? Now, in the second set, you can have any number of elements. Now, first of all, that should be a function. Now, if it has to be a function, then every element in set A should have a mapping in set B. That is our prerequisite condition for any relation to be a function, right? Then, when you are substituting the elements in set A in the function, then the answer what you are getting, we are calling them as images. Now, all those images what you are getting will form the range of the given function. Now, let us see this with a diagram, right? You have set A, children. Now, in this set A, you have some elements 1, 2, 3, 4. Okay. Then I am taking the second set as B, right? In this, I have elements as P, Q, R, S, and T. Now, what is the condition we were talking of? We were talking like every element in set A should have a mapping with some element in set B, right? So first set and second set, as we were talking previously, that is first set will be domain and the second set will be codomain. Now here we are defining a function over these two sets. Then how is this function? 1 is mapped to R, okay, 2 is mapped to P, 3 is mapped to Q, 4 is mapped to S. See, you may have a doubt, madam, why you are not relating the first element with first element? Why not second with second and so on? Wantedly, I have taken this example just to give a clear picture what exactly this means. The first element which is placed in set A may not be related to the first element itself. See, this we are placing, that's all. It can be anywhere inside the set, right? So 1, 2, 3, 4, all the elements, whatever you have in set A, they have a mapping in set B. All right. So can I say R is the image of 1? Can we say, children? According to the definition of image, right? It is an image, right? So R is image of 1. Then what is what is A? A will be what is 1? 1 will be
Madam,
the
please check
pre-image
your
of
audio
R.
once.
Yes, madam, it is working.
Now, is it clear, madam? Hello?
Yes, Usha madam, yes.
Right. Now, so here, what all images you have in set B, right? If we can form a set, then it gives you the range of the function, right? So in the codomain, you will find range. In the codomain, you will find range. Now, the next doubt what you may get is it that every time range and codomain, how they are related? Can we get a case like where we have range and codomain to be equal? Yes. Range is a subset of codomain. Subset, or sometimes it may be equal to codomain also if every element in the codomain it has got some relation with the some elements in set A, right children? So it can be a subset or it can be equal to the codomain. Hope that all the definitions what we have discussed till now are clear to you. Then next we are going to talk something about types of functions. Till now we were defining what is a function. In function, what are the different terms what we were using, right? What are the terms we were using? Domain, codomain, image, pre-image, and also range. Okay. Now, in types of functions, the first type what we are talking is injection or one-one function. Injection or one-one function, right? So, what is this one-one function? F maps A to B is a function. It is called as an injection or a one-one if distinct elements of A have distinct images in B. Distinct elements of A have distinct elements in B. What does it mean? Distinct element, that means every element in set A should have only one image in set B. Got it, children? And the images what you are getting, each and every element in set A should have a different image. The terms which are there in set A cannot have the same image like what we have seen as the third example in relation, right? We have seen many to one. It's not like that. It should be only one related to one element. Now let us see this diagrammatically. You have set A, children. 1, 2, 3, 4 are the elements, and set B, P, Q, R, S, T are the elements what we are taking. Then first set is the domain, second set is codomain, right? You are defining a function f over this. Then f in set A, 1 is mapped or it is related to Q, 2 is mapped to P, 3 is mapped to S, and 4 is mapped to R. Now see the conditions. Is it a function first of all? Yes, it is a function because every element in set A has got some image in set B. And the second condition, see, first of all, to call it as a one-one function, it should be a function first of all. Then what is that condition which is to be satisfied by the function to become a one-one function is every element in set A should have only one image. See, 1 is mapped to Q. That means it has got only one image. Every element has got only single image. And image of 1 is not equal to image of 2. Observe that, right? So this is the condition for a one-one function or an injection. So here is a condition how to check. If F maps A to B is a one-one, then suppose if you are taking two elements A1 and A2 from set A at random, then if f of A1 and f of A2 are equal, what are f of A1 and f of A2? F of A1 is nothing but image of A1. This is image of A2. If two images are equal, automatically the elements also should be equal. That is A1 and A2, the pre-images of these two should be equal. That means for A1 and A2 belongs to A. And if f of a1 is equal to f of a2, it implies that a1 is equal to a2. Now, for a given problem, if you check this condition, if this condition is satisfied, then we can say the function is 1, 1 function. Now, the next type of function is surjection or onto function. A function f maps a to b is said to be a surjection or onto function if the range of f is equal to the codomain of f. Just now I was discussing, isn't it? Can we have codomain and range to be equal? Yes, in this case, both of them should be equal. That means any function to become an onto function, codomain and range should be equal. Let us see with an example. Now set A with elements 1, 2, 3. We are taking set B with elements P, Q, R and S, right? Now, first set, as we know, it is domain and the second one codomain. We are defining a function f. 1 is mapped to S, 2 is mapped to Q, 3 is mapped to P, 4 is mapped to R. Now, observe this carefully, children. The codomain has got elements as PQRS. Range is also PQRS. So range and codomain both are equal, right? So we can say this is an onto function. And moreover, first, before checking onto function, you need to check the condition of a function, right? What is that condition? First, we need to check every element in set A should have a mapping in set B. Then the second condition, we can also check onto like this. Every element in set B has got a pre-image in set A. What does it mean? See, if I am taking an element P, it should have a relation in set A. It should have a mapping in set A, which we call it as pre-image. So every element in set A should have a pre-image in set B. So we can also define this as F maps A to B is onto if and only if for every B belongs to B, there exists A belongs to A such that f of A is equal to B. What does it mean? For every B belongs to B, that means for every element which is there in second set, you should always have one element in A, in set A, such that the element when substituted in the function gives you B, which is there in the second set, right? And I want to make one more point clear, children. These are the new symbols what you are using, right? This, E in a reverse direction. This is standing for there exist, okay? And belongs to symbol, you know already this is belongs to, right? If we are changing the direction of that belongs to, this stands for such that. Okay, I want you to get acquainted with the symbols also. That's the reason why I have made use of the symbols. There exist, A belongs to A such that f of A is equal to B. I think the symbols are clear to you now. Right. Now the next type of function is bijection or 1, 1 onto function. See, the name itself is telling you clearly that means the function should be 1, 1 and also onto. If a function is satisfying both the conditions, then we call it as a bijection. Now f maps A to B is both an injection, and a surjection. Injection, it is 1, 1. Surjection, it is onto. Then F is said to be a bijection from set A to set B. All right. So we will try to understand the same with an example. Set A, we have 5 elements, children, 1, 2, 3, 4, 5. And set B, I am taking P, Q, R, S, T. All right. Then we are defining the function f over these two sets. 1 is related to T, 2 is related to S, 3 is related to R, 4 is related to Q, and 5 it is mapped to P. Now clearly, every element in set A has got some mapping in set B. It is a function. And each and every element what you have in set A has got one and only one image in set B. Therefore, it is 1, 1. Next, every element in set B has got a pre-image in set A. Otherwise, we can say the codomain and range of this function both are equal. That should be an onto function, right? So this example states it is a 1, 1 function and an onto function. Therefore, I can call it as a bijection. Hope I'm clear? Right. So for a bijection, we need to check two conditions, children, as we were discussing previously. So F maps A to B is 1, 1. If and only if A1 comma A2 belongs to A and F of A1 equal to F of A2, it implies A1 is equal to A2. And the second condition what we have is F maps A to B is an onto function if and only if for every B belongs to B, there exists A belongs to A such that F of A is equal to B. Right, these are the three different types of functions what we have seen. And then the next concept is composite function. Now, till now, we were talking of a single function, right? When we talk of a composite function, we will take two or more functions and we will try to have some relation between the functions. How it is defined, let us see. Composite function. F maps A to B and G maps B to C. We have two functions, two different functions, right? F has got mapped from A to B and G is from B to C. What are these A, B, C? They are three different sets. Then these two are any two functions. Then A comma G of F of A such that A belongs to A is called a composite function of G with F and is denoted as G circle F. Now, what is that you are doing here? First, we will try to understand this in bits and pieces, then we will try to assemble the things. Right, what is this F of A? First, you are taking an element from set A. You are substituting in this function to get F of A. Right, where will be this F of A? F of A will be in B. Now, how is this B? This B is related to C. Got it? It has got a mapping to C. So, this F of A, that means an element which is there in B, you are substituting in the function G to get G of F of A. Where will be G of F of A? It should be in C. Right? So, if you can write order pairs like A comma G of F of A, all such order pairs, if you are putting that in a set, it gives you a composite function. And how is this composite function defined? It is a composite function of G with F. If it is F with G, also you can have, isn't it? So in that case, it should be F of G of A. In that case, you will call it as F circle G. All right. So now let us try to see this with a diagram. You have set A. In this set A, you're taking an element A. You have another set, it is set B. Over these two sets, you are defining a function F. Right? Now, this element A, if you're substituting in function F, then you are getting F of A. Where will be this F of A? F of A should be in B. So you call this as image of A. Then F of A, you can always call it as B. The B is nothing but an element in set B. We are taking the next set C. B and C, they over these two sets, you are defining a function G. Then in this function G, in this function g, you are substituting f of a to get g of f of a. Then what is g of f of a? Instead of f of a, we can always substitute b, right? So g of b is nothing but c. So G circle f of a is equal to c. This is the composite function definition. Right? Now we will try to see some examples. Whatever we have discussed till now, let us try to have a small practice with a problem. You have a function f maps R to R. What is R? Real number set, right? So real number set to real number set. So f maps R to R and g maps R to R are two different functions, right? So if f maps R to R and g maps R to R are defined by f of x is equal to 4x minus 1 and g of x is equal to x square plus 2, then find the first one, G circle f of x, G circle f of a plus 1 by 4, F circle f of x, and the fourth one is G circle f of 0. All right. So now we'll go with the solution, children. What is that you are given with? You are given two functions f of x is equal to 4x minus 1 and g of x is equal to x square plus 2. Now, before we proceed with the problem further, I would like to draw your attention. Let us cast our mind a little back to recollect what we have studied in your 9th and 10th classes, right? See, when we were talking of a polynomial, right? Suppose if p of x is a polynomial, you were asked to calculate what is p of 1, p of 2, and so on. What you were doing at that time, right? You were just taking that 1 as p of 1. That 1 you will be substituting in the function or the polynomial what is given to you in the place of x. The same thing we are trying to do here. There we called it as the value of a polynomial, right? So here again, we are going to implement the same thing in this problem, right? So the first bit is G circle f of x. As the definition says, G circle f of x is G of f of x. But what is f of x, children? 4x minus 1. So instead of f of x, we will substitute 4x minus 1. Got it? Then, now, how is it looking like? G of 4x minus 1. But what is the definition of g of x? It is x square plus 2. Now, if you have x here, you're defining it as x. Now, suppose if I put 1 here, then instead of x, you will substitute 1, right? That's what I was telling right now. So, instead of x, here you have 4x minus 1. That means, what is that you're doing? Instead of x, you will substitute 4x minus 1. So, you will get it as 4x minus 1 whole square plus 2. Now, how is this 4x minus 1 whole square looking like? It is a minus b whole square, isn't it? So 4x whole square, that is 16x square minus 8x plus 1, right? This is the expansion what you have for this bracket, and plus 2. Now 1 plus 2 here, it gives you 3. So you will get it as 16x square minus 8x plus 3 as your answer. All right. Now let us proceed with the next bit. That is, yeah, you are defined with the functions, that is f of x and g of x. Then G circle f of a plus 1 by 4. Just now we have calculated G circle f of x. What is G circle f of x, children? It is also a function, right? Now the function is 16x square minus 8x plus 3. Now this bit can be solved in two different ways. We will first discuss with one method, then I'll talk of the other method also, right? So here I can take directly this function and I can substitute wherever I have x, I can substitute A plus 1 by 4. Okay, so we'll just see 16 into A plus 1 by 4 whole square minus 8 into A plus 1 by 4 plus 3. What did we do? We have taken this and we have just, instead of x, we have substituted this value. All right, then 16 into a square plus 2a plus 1 by 16 minus 8 into a plus 1 by 4 plus 3. See, what is this expansion? This is a plus 1 whole square. 4 square is 16. Right, children? So 16 and 16, they get cancelled. And here 4 ones and 4 twos, 8. All right. Then you will have it as a square plus 2a plus 1 minus 2a. You are multiplying 2 with a, right? Minus 2a minus 2 plus 3. Then plus 2a and minus 2a, they get cancelled. And you will have it as a square minus a square. Look at this. 1 plus 3, which is 4. 4 minus 2 is plus 2. So you will have it as a square plus 2. Now, what is the other way of doing this problem? The other way is you can just take g of f of a plus 1 by 4. That a plus 1 by 4 you can substitute here. Whatever answer you are getting, again you will substitute in this function. Right? So that is one style of doing. As we have got this function value, we are directly making use of it. Hope I'm clear with this bit, right? Now let us see the next bit of the problem. You are given with the function, children, right? Now the next one is f circle f of x. F circle f of x is nothing but f of x. What is f of x? It is 4x minus 1. So we are just substituting instead of this. Now f of 4x minus 1, that means you will take this function. Wherever you have x, you will substitute 4x minus 1. So you will have it as 4 into 4x minus 1, which is 16x minus 4 minus 1. So it is 16x minus 5. So f circle f of x is 16x minus 5. All right. Now the last bit of this problem is g circle f of 0. So how do you write this? G of f circle f of 0. Now let us consider f circle f of x. Just now we got the answer as 16x minus 5. Now what is that you have? F circle f of 0. So wherever you have x, you will substitute 0. So 16 into 0 minus 5, which is nothing but minus 5. So instead of f circle f of 0, we can just replace it with minus 5. So what is that you will be getting, children? You will have it as g of minus 5. What is g of minus 5? In this function, we will substitute minus 5 in the place of x. So you have it as minus 5 whole square plus 2. Minus 5 whole square, which is 25, plus 2, which is nothing but 27. Right? So this is an example, children. Let us quickly move to the theorems which are based on the types of functions what we have seen. Now, F maps A to B and G maps B to C are any two injections. It is one function, right? Then G circle F maps A to C is also an injection. This is what we need to prove. That means you are given with two 1-1 functions, right? Then the composite function of G with F is also an injection. This is what we need to prove. Now, let us take A1 and A2 as two elements from set A. Then F maps A to B. What does it imply? F of A1 and F of A2 belong to B. That means first elements A1 and A2 are coming from the first set. F of A1 and F of A2 are the images of A1 and A2. Images will be in the second set, isn't it? They will be in the codomain. All right. Then let us see this. A is a set with elements A1 and A2. and B is a set with f of a1. On A and B, we are defining a function f. So in set B, you have f of a1 and f of a2. They are nothing but the images of elements a1 and a2, right? A1 is mapped to f of a1, a2 is mapped to f of a2. Then you have a function g maps b to c, right? And then see, g of f of a1 and g of f of a2 belongs to c. How is it? We will look into this. You have set c over the over set b and c. You are defining g. In b, what do you have, children? F of a1. So this f of a1 you are substituting in g. So you will get g of f of a1. All right. Now, if you substitute f of a2, then you will get g of f of a2. Hope this is clear. So, can we say g of f of a1 as g circle f of a1? Isn't it? We can say that, right? So this implies g circle f of a1 and g circle f of a2, they belong to set C. Further to continue with, see, when we were discussing 1 and onto functions, we have seen some conditions. We will try to make use of that in the problem now. Let us consider g circle f of a1 is equal to g circle f of a2, right? Then g of f of a1 is equal to g of f of a2. This implies g of f of a1 equal to g of f of a2. This is how we will write g circle f, isn't it? Now, what is given to you, children? G is an injection, that is 1 function. Now, if it is 1 function, if g of f of a1 is equal to g of f of a2, that means the images are equal. That means even the element, the pre-images should be equal. That is the condition for 1. So this implies f of a1 is equal to f of a2, right? So here, the next step, we can replace this with f of a1 is equal to f of a2, making use of this condition. But we are also given that f is a 1 function. So if f is a 1 function, the images f of a1 and f of a2 are equal. It means the pre-images of f of a1 and f of a2 also should be equal. That means a1 must be equal to a2. So here again, this implies a1 is equal to a2. Where did we start with? G circle f of a1 is equal to G circle f of a2. But what is that we have proved? A1 is equal to a2. It means we can conclude saying that G circle f maps A to C is a 1 function. All right, children. Now, let us quickly move to the next theorem. That is, if F maps A to B and G maps B to C are any two surjections. They are any two surjections. What do you mean by surjection? It is an onto function. Then G circle F maps A to C is also a surjection. This is what we need to prove now, right? So let us say take an element C belongs to C. Now we are given that G maps B to C is an onto function, right? It is a surjection. Other name for onto is surjection. Don't get confused, okay? So G maps B to C is a surjection. What does it mean, children? For every C belongs to C, there exists B belongs to B such that G of B is equal to C. This is what is the definition of an onto function. Not only that, you are given with F is a onto function. So F maps A to B is a surjection. It means for every B belongs to B, there exists A belongs to A such that F of A equal to B. What are we doing here? Simply we are trying to define what exactly is the meaning of an onto function, right? So let us look into this. You have set A with element A, set B with on which you are defining a function f on A and B. Then if you substitute A in function f, you are getting element B which is there in set B. that B is nothing but f of A. All right. Now you have set C, right? Over which you are on B and C, you are defining the function G, right? In G, you are substituting B to get the answer as C. When I say you're substituting B, what does it mean? You are substituting f of A. G of f of A is nothing but C, or you can say G of B is equal to C, right? So G circle f of A is equal to C. All right. Now let us come to the representation of this in the form of statements. So C is equal to G of B. Can we say C is equal to G of B from this, right? So instead of B, we are substituting f of A. Instead of B, you're substituting f of A, like how we got here, right? Then how is this G and F are related? How do you define it as a composite function? G circle F of A, right? So what is that you are getting? G circle F of A is equal to C, isn't it? So we can say for every C belongs to C, there exists A belongs to A such that G circle F of A is equal to C. Therefore, we can conclude saying that G circle F maps A to C is a surjection or an onto function. Right? Now, we are going to take the next theorem, which is a combination of these two theorems, children. You have two functions, F maps A to B, G maps B to C. These two are two bijections. What do you mean by bijection? They are 1, 1 and also on 2. That means F is 1, 1 and on 2. G is 1, 1 on 2. Okay. Then G circle F maps A to C is also a bijection. G circle F maps A to C is also a bijection.
Usha
Now let
madam,
us continue with the proof. Madam?
can we take up this session after political science? You can explain this theorem. Even students were asking. One student asked, "What is a bijection?" She asked you to repeat.
Okay.
So you can repeat bijection and also start with this theorem in the next session.
Okay, madam.
Okay. So you please go to the practice section, and then we'll come back.
Okay, right.
Thank you, ma'am.
Now, we'll continue with the class after some time, children. Meanwhile, I want you to take the screenshot of the practice questions, right? Before you take up these practice questions, we'll have a discussion on this bijective function and also the theorem. Don't worry about that. Please take a screenshot. We have discussed what is G circle F and so on, right? So you can keep practicing these problems. If you have any doubts in that, you can always leave your message in the chat box. We will address your doubts.
Thank you so much, Usha madam. It was a wonderful session as always. And there is a student from Punjab board, and he says that even in Punjab, according to the Punjab board textbook, this is the first part 1 of first year notes, functions, mathematical induction and all.
Okay.
So not only from our state, even from other states, students are viewing your class and they're getting benefited. I'm so happy for them.
Yeah.
I'm sorry that I had to stop you in between, not for the to just disturb the continuity, but I thought you can explain even these practice questions in detail in the coming session. Thank you so much, madam. Children,
All right, madam.
please tune in for
Yeah.
some more discussion on mathematics today. Thank you so much.
Thank you, ma'am.